Right now, at this very moment, you exist in a universe that began 13.8 billion years ago in an explosion of spacetime itself. We call it the Big Bang, imagining it as the ultimate beginning, the moment when time, space, matter, and energy burst into existence from nothing. But here's what makes this deeply unsettling. The Big Bang wasn't the beginning at all. It was a transition, a phase change in something far more ancient and mysterious than we ever imagined. For decades, we've comforted ourselves with the story that the Big Bang marked time zero, the absolute start of everything. This narrative allowed us to avoid the most disturbing question in all of science. What came before? We convinced ourselves that before had no meaning when time itself began. We were avoiding a truth so profound it challenges every assumption about existence, causality, and the nature of reality itself. Here is what recent discoveries have revealed. The Big Bang was not the birth of time, but the death of whatever came before it. The cosmic microwave background radiation, the afterglow of creation itself, contains patterns that can only be explained if our universe emerged from a pre-existing cosmic state. The quantum fluctuations frozen into the fabric of space carry information about conditions that existed before space-time as we know it began. Tonight, we're venturing beyond the cosmic horizon to explore the realm that preceded our reality. We're investigating theories that suggest time itself might be cyclical, that our universe could be one bubble in an infinite multiverse, that what we call the beginning might actually be the middle of an eternal cosmic story. Recent observations from the Planck satellite and gravitational wave detectors have provided unprecedented clues about these primordial conditions. Dr. Alan Guth, whose work on cosmic inflation earned him recognition as one of the most important cosmologists of our time, has proposed that our Big Bang was triggered by the collapse of a previous cosmic epoch. The mathematics of eternal inflation suggest that Big Bangs happen constantly throughout an infinite cosmic landscape, with each universe representing just one bubble in an eternally expanding multiverse. You might think these questions are purely academic, removed from your daily existence by billions of years and impossible distances. But understanding what came before the Big Bang directly impacts how we understand consciousness, free will, the meaning of existence, and humanity's place in the cosmic story. If our universe had a true beginning, we might be special. If it's just one episode in an eternal cosmic cycle, everything changes. What does it mean for causality if effects can precede their causes on cosmic scales? How do we understand the arrow of time if time itself is cyclical? What happens to the concept of uniqueness if infinite universes contain infinite copies of you living slightly different versions of your life? These aren't just philosophical puzzles. They read the inevitable consequences of taking our best scientific theories about pre-Big Bang cosmology to their logical conclusions. We'll discover how quantum mechanics suggests that nothing is actually the most violently creative state possible, constantly birthing virtual particles and potentially entire universes. We'll explore how the laws of physics themselves might evolve and change, making each cosmic cycle fundamentally different from the last. We'll investigate the possibility that consciousness itself might be a cosmic force, playing a role in determining which universes actually exist. The journey ahead will reveal that the question, what came before the Big Bang, leads directly to the deepest mysteries of existence. Why is there something rather than nothing? How does consciousness emerge from matter? What determines which mathematical possibilities become physical realities? These questions have haunted philosophers for millennia, but modern cosmology is finally providing scientific frameworks for approaching them. Stephen Hawking spent his final years working on these problems, developing theories about how the universe could be eternal and self-creating while still having apparent beginnings like the Big Bang. His no-boundary proposal suggests that asking what came before the Big Bang is like asking what is north of the North Pole. Not impossible, but requiring a fundamental reconceptualization of the question itself. The implications of pre-Big Bang cosmology extend into every aspect of human existence. If our universe is cyclic, then everything you've ever done has happened infinite times before and will happen infinite times again. If we exist in a multiverse, then every choice you don't make is made by other versions of you in parallel realities. If consciousness plays a role in cosmic evolution, then your awareness might be participating in the universe's method for understanding itself. You all understand why some physicists believe that exploring pre-Big Bang cosmology is more important than any other scientific endeavor. You will discover why the patterns we observe in cosmic structure today can only be explained by events that occurred in cosmic epochs whose existence challenges our most basic assumptions about time, causality, and existence. If you're ready to journey beyond the ultimate cosmic horizon into the realm that preceded everything we call reality, subscribe and hit the thumbs up button. And here is a question that will haunt you by the end of this exploration. If our Big Bang was just one event in an eternal cosmic cycle, what does that make you? A temporary arrangement of atoms, or an eternal pattern of information destined to repeat forever across infinite cosmic epochs? The path ahead leads us through increasingly strange territories where our most fundamental concepts about beginning and ending, cause and effect, existence and non-existence break down completely. We'll encounter realms where mathematics becomes reality, where consciousness might be as fundamental as matter and energy, where the act of observation might determine which universes exist. These aren't science fiction scenarios. They reveal the inevitable implications of our most successful theories about the nature of reality when pushed to their ultimate limits. The cosmic story doesn't begin with the Big Bang, but merely continues through it, carrying forward information and patterns from cosmic epochs whose very existence redefines what it means to exist. Now let's begin this journey beyond the cosmic veil, where the familiar concepts of time and causality give way to something far stranger and more beautiful than human language can properly describe. Chapter 1. Time's Prison. The moment we ask what came before the Big Bang, we confront the most fundamental limitation of human thought, our imprisonment within time's arrow. Every concept we possess about cause and effect, beginning and ending, existence and non-existence assumes that time flows in one direction from past to future. But approaching the Big Bang forces us to question whether time itself has the properties we imagine, or whether our cosmic origin story has been constrained by the temporal prejudices of minds evolved within a single universe. Dr. Carlo Rovelli, whose work on the physics of time has revolutionized our understanding of temporal flow, argues that time is not the universal backdrop against which events unfold, but an emergent property of complex systems. From this perspective, asking what came before the Big Bang is like asking what's north of the North Pole. Not impossible, but requiring a fundamental shift in how we conceptualize the question itself. The mathematics of general relativity reveals that time and space are inextricably linked in a four-dimensional space-time continuum. Einstein's field equations describe how matter and energy curve this space-time, creating what we experience as gravitational force. But they also predict that under extreme conditions, like those present at the Big Bang space-time itself, can undergo phase transitions that fundamentally alter its structure. Consider the cosmic microwave background radiation, the afterglow of the Big Bang, discovered by Arno Penzias and Robert Wilson in 1965. This radiation provides a snapshot of the universe when it was only 380,000 years old and first became transparent to light. The temperature fluctuations in this cosmic afterglow follow a nearly perfect black body spectrum. But embedded within this smoothness are tiny variations that can only be explained by quantum fluctuations that existed before the Big Bang itself. The Planck satellite mission, completed in 2018, mapped these temperature variations with unprecedented precision. The data reveals patterns that cosmologists call anomalies, Features in the cosmic microwave background that don't match what we'd expect if the Big Bang represented a true beginning. These anomalies suggest that our observable universe inherited structure from whatever cosmic state preceded it. Inflation theory, developed by Alan Guth in 1980, attempts to explain these observations by proposing that the very early universe underwent a period of exponential expansion. During this inflationary epoch, quantum fluctuations were stretched from subatomic to cosmic scales, creating the seeds for all the structure we observe today. But inflation itself raises profound questions about what came before, what triggered inflation to begin, and what stopped it from continuing forever. The mathematics of inflation suggests that once it starts, inflation should be eternal. In most regions of space, the inflationary field continues driving exponential expansion forever. Only in rare regions like our observable universe does inflation end, allowing normal cosmic evolution to proceed. This eternal inflation scenario implies that Big Bangs happen constantly throughout an infinite cosmic landscape, with each universe representing just one bubble in an ever-expanding multiverse. From this perspective, our Big Bang wasn't a beginning, but a local event within an eternal cosmic process. The question, what came before, becomes what happens in other regions of the eternal inflating landscape. Our universe emerges not from nothing, but from the ongoing dynamics of a cosmic process that has no beginning and will have no end. But eternal inflation faces its own temporal paradoxes. If inflation has been going on forever, then every possible arrangement of matter and energy should have occurred infinite times throughout the infinite cosmic landscape. This leads to what cosmologists call the measure problem. How do we calculate probabilities in an infinite multiverse where every possible event happens infinitely often? Recent work by physicist Sean Carroll suggests that the measure problem might be resolved by considering the quantum mechanical nature of the multiverse. Instead of classical eternal inflation, the cosmic landscape might be governed by quantum superposition, where all possible cosmic histories exist simultaneously until observation causes specific outcomes to become manifest. This quantum approach to cosmology transforms the question of what came before the Big Bang into a question about quantum measurement and the nature of observation itself. If cosmic histories exist in superposition, then the Big Bang might represent not a temporal beginning, but a moment when quantum possibilities crystallize into classical reality. The temporal structure of pre-Big Bang cosmology also raises profound questions about causality and determinism. In our everyday experience, causes precede effects in a clear temporal sequence. But if time itself emerges from more fundamental processes, then the causal relationships we observe might be emergent properties rather than fundamental features of reality. Loop quantum cosmology, developed by Abhay Ashtekar and others, provides a concrete framework for investigating these questions. In this approach, the Big Bang singularity, where general relativity predicts infinite density and curvature, is replaced by a quantum bounce, where a previous contracting universe transitions smoothly into our expanding universe. The bounce occurs because quantum effects prevent matter from compressing beyond the Planck density. From the loop quantum cosmology perspective, what came before the Big Bang was a previous cosmic cycle that reached maximum compression and then began expanding again. Our universe inherits information about this previous cycle through quantum correlations that survive the bounce. The cosmic microwave background anomalies might be direct observational evidence of structure in the pre-bounce universe. But even cyclic cosmology faces temporal puzzles. If cosmic cycles repeat eternally, with each cycle lasting roughly 100 billion years, then time becomes cyclical rather than linear. Past and future lose their absolute meaning. What we call before might actually be after from a different temporal perspective. The question of cosmic origins becomes not, when did everything begin? But how do we navigate cyclical time? String theory offers another approach to pre-Big Bang cosmology through its description of fundamental interactions. In string theory, the Big Bang might represent a collision between higher dimensional spaces called branes. Before the collision, these branes existed in a higher dimensional bulk space, following their own evolutionary dynamics. Our Big Bang occurs when two branes collide, creating the four-dimensional spacetime we inhabit. This ekpyrotic scenario, developed by Neil Turok and Paul Steinhardt, suggests that what came before the Big Bang was the approach phase of this higher dimensional collision. The cosmic structure we observe today originated as quantum fluctuations in the higher dimensional brane dynamics. From this perspective, time extends infinitely into the past through cycles of brane collision and separation. The temporal aspects of pre-Big Bang cosmology also connect to fundamental questions about the nature of consciousness and observation. If time is emergent rather than fundamental, then consciousness, which seems intimately connected to temporal experience, might play a more fundamental role in cosmic evolution than we've previously imagined. Some interpretations of quantum cosmology suggest that observation might be necessary to collapse cosmic wave functions and determine which possible cosmic histories become actual. From this perspective, consciousness doesn't just observe the universe, it participates in determining which universe exists to be observed. As we confront the limitations of temporal thinking and explore cosmic models where time itself becomes flexible, we approach one of the deepest questions in all of science: whether existence requires a beginning, or whether the concept of beginning itself might be a limitation of minds trapped within linear time. The answer challenges not just our understanding of cosmology, but our most basic assumptions about causality, existence, and the nature of reality itself. Breaking free from time's prison requires abandoning the assumption that temporal sequence provides the fundamental structure of existence. What lies beyond this assumption takes us into realms where cause and effect become fluid, where beginning and ending lose their meaning, and where the very concept of before transforms into something unrecognizably strange. Chapter 2. Quantum Genesis. In the realm that preceded our Big Bang, the familiar distinction between something and nothing dissolves into quantum uncertainty. Here, the vacuum itself becomes the most creative force in existence, not empty space waiting to be filled, but a seething ocean of virtual particles and quantum fluctuations that contains the seeds of infinite universes. Understanding quantum genesis requires abandoning our everyday intuitions about creation and recognizing that nothing might be the most unstable state possible. Quantum field theory reveals that what we call empty space is actually filled with quantum fields fluctuating at all possible frequencies. These fluctuations normally cancel out over macroscopic scales, creating the illusion of empty vacuum. But in the extreme conditions that preceded the Big Bang, these quantum fluctuations become amplified and stretched until they manifest as real particles and genuine spacetime curvature. Dr. Alexander Vilenkin, whose work on quantum cosmology has provided mathematical frameworks for understanding cosmic origins, demonstrated that quantum tunneling can create universes from literally nothing. His calculations show that a quantum fluctuation can spontaneously produce a small region of inflating spacetime that grows into a full universe. This process requires no pre-existing matter, energy, or even spacetime. It emerges from the quantum uncertainty inherent in the laws of physics themselves. The mathematics of this quantum genesis follows from Heisenberg's uncertainty principle, which states that energy and time cannot both be precisely determined simultaneously. This uncertainty allows for the temporary borrowing of enormous amounts of energy from the quantum vacuum, provided this energy is repaid quickly enough. But if the borrowed energy goes into creating inflating spacetime, the inflation itself stretches the repayment time, potentially allowing the energy debt to become permanent. Recent calculations by physicist Sean Carroll and his collaborators have shown that this quantum tunneling process should happen continuously throughout eternal time. If the laws of quantum mechanics apply at the most fundamental level, then universes should be spontaneously generated from quantum vacuum fluctuations at a constant rate. Our Big Bang represents just one such quantum genesis event in an infinite sequence. But quantum genesis raises profound questions about the nature of the laws of physics themselves. If universes can be created from nothing through quantum processes, what determines which laws of physics govern each newly created universe? The fundamental constants that define our reality, the strength of gravity, the mass of the electron. The speed of light might be accidents of our particular quantum genesis event rather than universal truths. String theory provides a framework for understanding this variability of physical laws. In string theory, the fundamental constants are determined by how extra-spatial dimensions are curled up into tiny geometric shapes called Calabi-Yau manifolds. Different compactifications produce different values for physical constants, creating a vast landscape of possible universes with different physics. The string theory landscape contains approximately 10,500 different possible compactifications, each corresponding to a universe with different physical laws. Quantum genesis might randomly select which compactification becomes manifest in each newly created universe. From this perspective, our physical laws are an inevitable consequences of some deeper principle. They read contingent outcomes of our particular quantum genesis event. This randomness in quantum genesis connects to the anthropic principle, the observation that our universe as physical constants seem fine-tuned for the form toda, existence of complex structures like galaxies, stars, and life. If constants were slightly different, atoms couldn't form stable bonds, stars couldn't shine, and galaxies couldn't condense from primordial matter. The precise balance required for complexity seems improbably perfect. But if quantum genesis creates infinite universes with random physical constants, then the fine-tuning problem disappears. Most universes would indeed be sterile, with constants that don't permit complexity. But some universes like ours would randomly receive constants compatible with structure formation. We observe fine-tuning not because the universe was designed for us, but because we could only evolve in a universe compatible with our existence. The quantum mechanical nature of cosmic genesis also suggests that the process might be fundamentally indeterministic. Unlike classical physics, where identical initial conditions produce identical outcomes, quantum mechanics is inherently probabilistic. Each quantum genesis event produces a universe with randomly determined properties, creating an infinite ensemble of possible realities. This quantum indeterminacy raises fascinating questions about the relationship between mathematics and physical reality. If all mathematically possible universes are generated through quantum genesis, then mathematics might be more fundamental than physics. Physical reality becomes the subset of mathematical reality that happens to be instantiated through quantum processes. Physicist Max Tegmark has proposed that this relationship between mathematics and physics might be even deeper. In his mathematical universe hypothesis, all mathematically consistent structures exist as physical reality. From this perspective, quantum genesis doesn't create universes. It selects which pre-existing mathematical structures become observable by conscious beings. The observational consequences of quantum genesis extend into the structure of our own cosmic microwave background radiation. If our Big Bang emerged from quantum vacuum fluctuations, then the initial conditions for cosmic evolution should reflect the statistical properties of quantum noise. The nearly Gaussian distribution of temperature fluctuations in the cosmic microwave background matches what we'd expect from quantum genesis, providing potential observational evidence for this scenario. Recent analysis of Planck satellite data has revealed subtle, non-Gaussian features in the cosmic microwave background that might encode information about the quantum genesis process itself. These features, called primordial non-Gaussianities, could provide direct observational access to the quantum mechanical processes that created our universe. But quantum genesis also faces theoretical challenges that push our understanding to its limits. The process requires the spontaneous creation of enormous amounts of energy from quantum vacuum fluctuations. While quantum mechanics permits such energy creation through uncertainty principle, scaling this up to cosmic proportions requires theories of quantum gravity that remain largely speculative. Loop quantum cosmology provides one approach to understanding quantum genesis through its description of spacetime as fundamentally discrete rather than continuous. In this framework, quantum genesis might occur when quantum fluctuations in the discrete, geometric structure of spacetime reach sufficient amplitude to create new regions of expanding space. The discrete structure of spacetime in loop quantum cosmology also suggests that quantum genesis might be constrained by geometric limitations. Instead of arbitrary universe creation, the process might follow specific patterns determined by the quantum geometry of spacetime itself. This could lead to correlations between different universes created through quantum genesis. Another challenge comes from the measurement problem in quantum mechanics. If quantum genesis creates universes in superposition states existing in all possible configurations simultaneously, then what causes these superpositions to collapse into definite classical universes? The answer might require understanding how consciousness and observation relate to cosmic evolution. Some interpretations suggest that consciousness itself might play a role in quantum genesis by collapsing cosmic wave functions and determining which possible universes become actual. This participatory universe hypothesis proposes that observation and existence are inextricably linked, with consciousness serving as the mechanism that transforms quantum possibility into classical reality. The implications of quantum genesis extend far beyond cosmology to fundamental questions about existence, necessity, and contingency. If universes can spontaneously emerge from quantum nothingness, then existence itself becomes a quantum phenomenon rather than a classical fact. The question, why is there something rather than nothing, transforms into why do quantum laws permit something to emerge from nothing? As we explore the quantum foundations of cosmic genesis, we discover that creation itself operates according to principles that transcend our everyday concepts about causality and necessity. The realm that preceded our Big Bang wasn't empty nothingness waiting to be filled, but quantum creativity in its purest form, a realm where possibility and actuality merge in processes that continuously birth new realities from the fertile void of quantum uncertainty. Chapter 3. Infinite Recursion. The cosmic story we re-uncovering reveals a universe caught in infinite recursion. Each Big Bang emerging from the collapse of a previous cosmic epoch, which itself emerged from an earlier collapse extending backwards through an endless chain of cosmic cycles. This eternal return challenges every assumption we hold about uniqueness, progress, and meaning, suggesting that our universe is not a singular event, but one iteration in an infinite cosmic algorithm that has been running since before time had meaning. Dr. Paul Steinhardt, whose work on cyclic cosmology has provided mathematical frameworks for understanding eternal cosmic recurrence, proposes that the Big Bang represents a phase transition in an eternally oscillating universe. Each cycle begins with rapid expansion, proceeds through structure formation and cosmic evolution, reaches maximum expansion, then contracts back to a big crunch that triggers the next Big Bang. The process repeats indefinitely, with no beginning and no end. The mathematics of this cyclic model follows from modifications to Einstein's field equations that include scalar fields capable of driving both expansion and contraction. During the expansion phase, these fields behave like dark energy, accelerating cosmic expansion. But as the fields evolve, they eventually reverse sign, causing the expansion to slow, stop, and reverse into contraction. The contraction proceeds until quantum effects trigger a bounce that initiates the next expansion phase. Recent observations of Type Ia supernova have confirmed that our universe's expansion is indeed accelerating, driven by what cosmologists call dark energy. This acceleration matches what cyclic models predict during the expansion phase of each cosmic cycle. If the scalar field responsible for this acceleration eventually reverses, our universe might already be following the cyclic trajectory toward eventual contraction. But infinite recursion creates profound paradoxes about information and causality. If cosmic cycles repeat eternally, then every arrangement of matter and energy should occur infinite times throughout cosmic history. This means that identical copies of you have existed in infinite previous cycles and will exist in infinite future cycles. The patterns of neural activity that constitute your current thoughts and memories have been repeated countless times before and will be repeated countless times again. The implications extend beyond personal identity to questions about free will and determinism. If cosmic cycles repeat with perfect fidelity, then every choice you make has been made infinite times before by identical copies of yourself in previous cycles. Free will becomes meaningless when all possible choices have already been determined by infinite cosmic repetition. However, quantum mechanics suggests that cosmic cycles might not repeat with perfect fidelity. Quantum uncertainty ensures that each cycle unfolds slightly differently from previous iterations, creating what physicists call chaotic inflation, where small quantum fluctuations grow into large-scale differences between cycles. Your current existence might be unique, despite being one of infinite variations on similar themes. The observational evidence for infinite recursion comes from subtle features in the cosmic microwave background radiation that might encode information about previous cosmic cycles. Dr. Roger Penrose has identified what he calls Hawking points, circular patterns in the cosmic microwave background that might represent the evaporation of supermassive black holes from previous cosmic epochs. If these patterns are confirmed, they would provide direct observational evidence for cosmic cycles. Loop quantum cosmology provides a concrete framework for understanding how infinite recursion might operate through quantum bounces. In this approach, each cosmic cycle reaches maximum compression at the Planck density, approximately 1,096 kilograms per cubic meter, before quantum effects cause a bounce that initiates the next expansion phase. The bounce preserves information about the previous cycle structure, allowing patterns to propagate across cosmic epochs. Computer simulations of loop quantum cosmology have shown that quantum bounces can indeed preserve large-scale structure from one cycle to the next. Galaxy clusters, superclusters, and cosmic voids from previous cycles can survive the bounce and provide initial conditions for structure formation in subsequent cycles. The cosmic web we observe today might be inherited from the cosmic web of previous universes. But infinite recursion also raises questions about cosmic evolution and progress. If cycles repeat eternally, does the universe evolve or simply oscillate between the same states? Some models suggest that information can accumulate across cycles, allowing cosmic complexity to increase over infinite time. Each cycle might build upon the achievements of previous cycles, creating a form of cosmic evolution that transcends individual universes. String theory provides additional mechanisms for infinite recursion through its description of higher dimensional brain dynamics. In the ekpyrotic model developed by Neil Turok and Paul Steinhardt, our four-dimensional universe exists on a brane that periodically collides with a parallel brane in higher dimensional space. Each collision corresponds to a Big Bang, while the periods between collisions allow both branes to evolve and accumulate structure. The brane collision model suggests that what we interpret as cosmic cycles might actually be interactions between multiple universes existing in parallel within higher dimensional space. The infinite recursion occurs not within a single universe, but through eternal interactions between multiple universes that share the same higher dimensional bulk space. This perspective transforms the question of what came before the Big Bang into a question about what exists alongside our universe in higher dimensions. The pre-Big Bang state becomes the parallel universe that approaches collision with our cosmic brain. The collision itself represents the moment when these parallel realities merge temporarily before separating again to begin the next cycle. The anthropic implications of infinite recursion are particularly striking. If cosmic cycles repeat with variation, then every possible arrangement of physical constants should occur across different cycles. Most cycles would produce universes incompatible with complex structure formation, but some cycles would randomly generate constants suitable for galaxies, stars, and life. We observe a life-compatible universe not because it's special, but because we could only evolve in cycles compatible with our existence. Recent developments in eternal inflation theory suggest that infinite recursion might be even more complex than simple cosmic cycles. In chaotic inflation, developed by Andre Linde, different regions of space undergo inflation at different times, creating a fractal structure where Big Bangs occur continuously at different scales and times. Our universe becomes one bubble in an infinite foam of eternally inflating space. This eternal inflation scenario implies that infinite recursion operates not through temporal cycles, but through spatial multiplicity. New universes are constantly being born throughout infinite space, each with randomly determined physical constants and initial conditions. The question of what came before our Big Bang becomes the question of what happens in other regions of eternal inflationary space. The measurement problem in quantum mechanics adds another layer of complexity to infinite recursion. If cosmic cycles exist in quantum superposition simultaneously, following all possible evolutionary paths, then what causes specific outcomes to become manifest? Some interpretations suggest that consciousness itself might play a role in collapsing cosmic wave functions and determining which possible cycles become actual. The consciousness interpretation of cosmic cycles raises profound questions about the relationship between mind and cosmic evolution. If observation is necessary to actualize cosmic cycles, then consciousness becomes a cosmic force that participates in determining which universes exist. The infinite recursion becomes not just a mechanical process, but a creative collaboration between cosmic physics and conscious observation. As we confront the implications of infinite cosmic recursion, we discover that our existence becomes both utterly unique and endlessly repeated, both historically significant and cosmically inevitable. The patterns of matter and energy that constitute your current experience have danced this cosmic dance infinite times before and will continue dancing it infinite times into the future, each iteration slightly different but essentially similar. The universe reveals itself as an infinite cosmic algorithm, recursively generating new realities from the ashes of previous ones, carrying forward information and structure across timescales that dwarf human comprehension. Chapter 4. Eternal Mathematics. Beyond the physical processes that might have preceded our Big Bang lies an even more fundamental question. What determines which mathematical possibilities become physical realities? As we probe deeper into cosmic origins, we discover that the distinction between mathematics and physics begins to dissolve, revealing a universe where mathematical structures might be more fundamental than the matter and energy they describe. Dr. Max Tegmark's mathematical universe hypothesis proposes that physical reality consists entirely of mathematical structures, that what we call matter and energy are simply our perceptions of abstract mathematical relationships. From this perspective, the question of what came before the Big Bang transforms into the question of how mathematical structures become instantiated as observable universes. The evidence for this mathematical foundation of reality appears throughout physics. The laws of nature are expressed as mathematical equations that describe relationships between abstract quantities. These equations work with unreasonable effectiveness, predicting experimental outcomes with extraordinary precision. As physicist Eugene Wigner noted, the unreasonable effectiveness of mathematics in the natural sciences suggests that mathematics and physics might be more intimately connected than we typically assume. Consider the fundamental constants that define our universe: the speed of light, Planck's constant, the gravitational constant, the fine structure constant. These numbers appear to be arbitrary from a physical perspective. There is no obvious reason why they should have their observed values rather than some other values. But from a mathematical perspective, these constants might represent parameters in a vast space of possible mathematical structures. String theory provides a concrete framework for understanding this mathematical landscape. The theory predicts approximately 10,500 different possible compactifications of extra dimensions, each corresponding to a universe with different physical constants. This string landscape represents a tiny fraction of all possible mathematical structures, suggesting that the full space of possible realities might be vastly larger than even string theory encompasses. If all mathematical structures exist as physical realities, then what came before the Big Bang was the eternal existence of all possible mathematical relationships. Our universe represents one particular mathematical structure, one solution to a vast system of equations that includes all possible physical laws and initial conditions. The Big Bang becomes not the creation of our universe, but the moment when our particular mathematical structure becomes accessible to conscious observation. This mathematical realism solves several puzzles about cosmic fine-tuning and the anthropic principle. If all possible mathematical structures exist, then structures compatible with complex organization and consciousness exist alongside structures that are completely sterile. We observe a universe compatible with life, not because it's special, but because we could only evolve within mathematical structures that permit consciousness to emerge. The relationship between mathematics and consciousness becomes crucial in this framework. If reality consists of mathematical structures, then consciousness itself must be a mathematical phenomenon, a particular type of information processing pattern that can exist within certain mathematical contexts. The emergence of consciousness doesn't require special physical processes, but simply represents the instantiation of particular mathematical relationships. Recent developments in computational theory support this mathematical view of consciousness. The integrated information theory developed by Giulio Tononi quantifies consciousness in terms of mathematical measures like phi, which describes how much information a system integrates beyond what its parts could integrate independently. This suggests that consciousness might be substrate-independent, capable of existing in any mathematical structure that implements appropriate information integration patterns. If consciousness is mathematical, then it might exist throughout the eternal mathematical landscape, experiencing reality from countless different perspectives simultaneously. What we call our consciousness might be just one point of view within an infinite mathematical structure that contains every possible conscious experience. The quantum mechanical aspects of mathematical reality add additional layers of complexity. Quantum mechanics describes physical systems using mathematical objects called wave functions that exist in abstract mathematical spaces called Hilbert spaces. These wave functions evolve according to the Schrödinger equation, which is purely mathematical with no reference to physical processes. Some interpretations of quantum mechanics, like the many worlds theory, suggest that all possible solutions to the Schrödinger equation exist simultaneously as parallel realities. If this is correct, then quantum mechanics reveals the mathematical nature of reality directly, what we call Physical processes are actually explorations of mathematical possibility space. The multiverse theories we've discussed throughout our exploration of pre-Big Bang cosmology can all be understood as different aspects of eternal mathematical existence. Eternal inflation explores different regions of mathematical space through random quantum tunneling. Cyclic cosmology explores temporal relationships within mathematical structures. String theory explores different compactifications of higher dimensional mathematical geometries. From the mathematical universe perspective, these aren't competing theories, but complementary descriptions of how consciousness navigates through eternal mathematical reality. Each theory describes different aspects of the infinite mathematical landscape that has always existed and will always exist. But mathematical realism raises profound questions about the nature of existence and observation. If all mathematical structures exist, then why do we experience this particular reality rather than some other mathematical structure? The answer might involve understanding how consciousness selects which aspects of mathematical reality become accessible to experience. Some theories suggest that consciousness might function as a filter, selecting compatible mathematical structures from the infinite ensemble of possibilities. Your particular conscious experience might represent one path through mathematical space, with your choices and observations determining which mathematical relationships become manifest to your awareness. This connects to the measurement problem in quantum mechanics, which asks why quantum superpositions collapse into definite states when observed. If reality is fundamentally mathematical, then observation might represent the process by which consciousness selects specific mathematical relationships from the superposition of all possibilities. The computational aspects of mathematical reality suggest that what we call time might actually represent computational steps in the exploration of mathematical space. The evolution of physical systems according to natural laws becomes the execution of mathematical algorithms that explore different regions of possibility space. The Big Bang represents the initialization of one such computation. From this perspective, what came before the Big Bang was the eternal existence of the mathematical algorithm that our universe executes. The beginning of our universe corresponds to the start of this particular computation, but the mathematical structure it explores has always existed in the eternal realm of mathematical truth. Recent developments in digital physics support this computational view of reality. Researchers like Stephen Wolfram have demonstrated that simple computational rules can generate complex behaviors indistinguishable from physical processes. If reality is computational, then physics becomes applied mathematics, and mathematics becomes applied computation. The philosophical implications of eternal mathematics extend beyond physics to questions about meaning, purpose, and value. If all mathematical structures exist, then every possible story, every possible life, every possible achievement and tragedy exists somewhere in mathematical space. This might seem to drain life of meaning, but it might also suggest that meaning is as eternal and fundamental as the mathematical structures that contain it. Your current experience reading these words exists as a mathematical fact that is as eternal and unchangeable as the theorem that 2 2 equals 4. Your thoughts, feelings, and choices are permanent features of mathematical reality, preserved forever in the abstract structures that define all possible experiences. The question of what came before the Big Bang reveals itself as the question of how consciousness navigates eternal mathematical existence. The answer doesn't involve temporal precedence, but mathematical inclusion. We exist within mathematical structures that have always existed and will always exist, experiencing reality as conscious exploration of infinite mathematical truth. As we recognize the mathematical foundations of existence itself, we discover that we are not temporary arrangements of matter and energy, but eternal mathematical entities exploring the infinite landscape of possibility. Chapter 5. Consciousness creates, In the deepest theories about what preceded our Big Bang, consciousness emerges not as an accidental byproduct of complex chemistry, but as a fundamental force that participates in determining which possible universes become actual. This participatory universe hypothesis suggests that the act of observation doesn't just reveal reality, it helps create it, making consciousness a cosmic architect rather than a passive witness to cosmic evolution. Dr. John Wheeler, whose insights into quantum mechanics and cosmology shaped our understanding of reality's deepest levels, proposed that we live in a participatory universe where observation and existence are inextricably linked. His famous thought experiment involving delayed choice quantum measurements demonstrates that the act of observation can retroactively determine the nature of physical events, even when those events occurred in the distant past. The quantum mechanical foundations of this participatory universe lie in the measurement problem. The question of why quantum superpositions collapse into definite states when observed. In standard quantum mechanics, particles exist in superposition states containing all possible properties simultaneously until measurement causes these superpositions to collapse into specific outcomes. But what constitutes a measurement, and why does observation have this special role? Recent developments in quantum foundations suggest that consciousness itself might be the mechanism that collapses quantum wave functions. The von Neumann-Wigner interpretation of quantum mechanics proposes that consciousness is the only thing that can cause wave function collapse because it is the only non-physical entity capable of selecting specific outcomes from quantum superpositions. If consciousness collapses wave functions, then conscious observation becomes a creative act rather than a passive recording. Each measurement doesn't just reveal pre-existing properties, but actualizes specific possibilities from the quantum realm of pure potentiality. Reality becomes a collaborative creation between the physical laws that generate possibilities and conscious observations that select which possibilities become actual. Scaling this up to cosmology creates profound implications for what preceded the Big Bang. If our universe exists in quantum superposition until observed, then conscious observation might be necessary to actualize cosmic history itself. The Big Bang might not be a past event that happened independently of observation, but a retroactive creation that occurs when conscious beings evolve enough to observe cosmic origins. Dr. Andre Lind, whose work on chaotic inflation has revolutionized cosmology, has explored how consciousness might relate to cosmic evolution. He suggests that consciousness and cosmos might co-evolve, with each cosmic epoch developing the information processing capacity necessary to observe and thereby actualize the next cosmic epoch. From this perspective, consciousness doesn't just emerge from cosmic evolution, it participates in driving cosmic evolution forward. The delayed choice nature of quantum measurement adds temporal complexity to this participatory cosmology. Wheeler, as delayed choice experiments demonstrate that measurements made today can retroactively determine the nature of events that occurred billions of years ago. If consciousness plays a role in cosmic evolution, then the conscious observations we make today might retroactively determine the nature of events that preceded the Big Bang. This creates what physicists call a closed causal loop, where cosmic evolution produces consciousness, which then retroactively actualizes the cosmic evolution that produced it. The universe becomes self-creating through the mediation of consciousness, a cosmic bootstrap, where effect precedes cause on the largest possible scales. Recent research in quantum biology has revealed that consciousness might already operate through quantum mechanical processes. Studies of microtubules in neurons, photosynthesis in plants, and navigation in birds have shown that biological systems routinely exploit quantum effects like superposition and entanglement. If consciousness is fundamentally quantum mechanical, then it might naturally interface with the quantum processes that determine cosmic evolution. The Global Consciousness Project, led by researcher Roger Nelson at Princeton University, has collected data suggesting that human consciousness might influence random quantum events on a global scale. During major world events that focus collective attention, quantum random number generators worldwide show statistical deviations from pure randomness. While controversial, this data hints that consciousness might indeed influence quantum processes. If consciousness influences quantum events, then the collective consciousness of all sentient beings throughout cosmic history might participate in determining cosmic evolution. Each conscious observation contributes to the ongoing selection of actual cosmic history from the superposition of all possible cosmic histories. The universe becomes a collaborative artwork created by the intersection of physical law and conscious choice. The anthropic principle takes on new meaning in this participatory framework. Instead of asking why the universe's physical constants are fine-tuned for life, we might ask how conscious observation of fine-tuning retroactively determines the values of physical constants. The constants aren't fine-tuned in advance. They become fine-tuned through the retroactive influence of conscious beings who evolve to observe them. This participatory anthropic principle resolves many puzzles about cosmic fine-tuning without requiring multiverse theories. We observe a life-compatible universe not because we're one lucky outcome among infinite possibilities, but because conscious observation of life compatibility retroactively actualizes the physical constants necessary for life to evolve and observe. The information-theoretic aspects of participatory cosmology suggest that consciousness might function as a cosmic information processing system. Each conscious observation collapses quantum superpositions and thereby processes information about which possibilities become actual. The evolution of consciousness throughout cosmic history represents the universe developing increasingly sophisticated information processing capabilities. From this perspective, what came before the Big Bang was a realm of pure quantum possibility, a cosmic superposition, containing all possible universes simultaneously. Conscious observation doesn't just reveal which possibility became actual. It participates in the selection process that determines actuality itself. The Big Bang represents the first moment when cosmic information processing became sufficient to begin actualizing specific possibilities. But participatory cosmology raises profound questions about the relationship between individual and cosmic consciousness. If your personal observations contribute to determining cosmic history, then your consciousness becomes cosmically significant, regardless of your apparent size relative to the universe. Every moment of awareness participates in the ongoing creation of reality. Some interpretations suggest that individual consciousnesses might be localized aspects of a cosmic consciousness that pervades the universe. The Buddhist concept of universal Buddha nature, the Hindu understanding of Atman as identical to Brahman, and the mystical traditions of all cultures describe consciousness as fundamentally one and cosmic in scope. Modern physics provides frameworks for understanding this cosmic consciousness through quantum field theory. If consciousness emerges from quantum field interactions in the brain, then it might be related to quantum fields that permeate all of space. Consciousness becomes not a local phenomenon, but a cosmic field that manifests differently at different locations. The participatory universe hypothesis also suggests that the evolution of consciousness might be the universe's method for understanding itself. Through the development of conscious observation, the universe gains the ability to collapse its own quantum superpositions and thereby determine its own nature. Cosmic evolution becomes cosmic self-creation mediated by conscious choice. Recent developments in quantum information theory support this view of consciousness as cosmic information processing. Quantum computers exploit superposition and entanglement to process information in ways that classical computers cannot match. If consciousness operates through quantum information processing, then it might have computational capabilities that transcend classical physical limitations. The implications of consciousness as cosmic creator extend beyond physics to questions about free will, moral responsibility, and the meaning of existence. If your conscious choices participate in determining cosmic reality, then you bear responsibility not just for your personal actions, but for your contribution to the ongoing creation of the universe itself. As we recognize consciousness as a cosmic force rather than a local accident, we discover that asking what came before the Big Bang leads inevitably to asking about the nature and role of consciousness in cosmic evolution. The answer reveals a universe where mind and matter, observer and observed, creator and creation are inextricably intertwined in the ongoing dance of cosmic self-actualization. The pre-Big Bang realm becomes not a physical state, but a state of pure possibility waiting for consciousness to actualize specific realities through the cosmic creative act of observation itself. Chapter 6. Higher Dimensions. Beyond the familiar 3 dimensions of space and 1 dimension of time that structure our everyday experience lies a vast multidimensional landscape where the events we interpret as cosmic origins unfold according to geometric principles that transcend human intuition. Understanding what came before the Big Bang requires recognizing that our 4-dimensional spacetime might be just a thin slice of a higher dimensional reality where cosmic creation operates through mechanisms invisible to creatures trapped within limited dimensional perspectives. String theory, our most mathematically sophisticated attempt to unify quantum mechanics with general relativity, requires the existence of additional spatial dimensions beyond the 3 we experience directly. The mathematics demands exactly 10 spatial dimensions plus 1 temporal dimension, creating an 11-dimensional universe where the familiar physics of our 4-dimensional experience emerges as a low-energy approximation of higher-dimensional string dynamics. Dr. Lisa Randall, whose work on extra-dimensional physics has revolutionized our understanding of cosmic architecture, proposes that our observable universe exists on a 3-dimensional brane, embedded within higher dimensional space called the bulk. From this perspective, what we call the Big Bang might represent a collision between our brane and another brane moving through the higher dimensional bulk space. The mathematics of brane cosmology suggests that these higher dimensional brane collisions occur regularly throughout cosmic history, with each collision corresponding to what lower dimensional beings, like ourselves, would observe as a Big Bang. What came before our Big Bang was the approach phase of this brane collision, during which both branes evolved according to higher dimensional dynamics invisible to creatures confined to 3 spatial dimensions. Recent calculations by Neil Turok, Paul Steinhardt, and their collaborators have shown that brane collisions can indeed produce the observed features of our cosmic microwave background radiation. The quantum fluctuations that seeded large-scale structure formation in our universe originated as fluctuations in the higher dimensional brane dynamics during the approach to collision. But higher dimensional physics reveals that even this picture might be too limited. M-theory, the most advanced version of string theory, suggests that fundamental reality might involve membranes of various dimensions, not just 3-dimensional branes, but also higher dimensional objects existing within 11-dimensional space. Our universe could be the result of interactions between membranes of different dimensionalities. The compactification of extra dimensions creates additional complexity in understanding pre-Big Bang conditions. The 6 extra spatial dimensions required by string theory must be compactified, curled up into tiny geometric shapes called Calabi-Yau manifolds that are too small to observe directly. But these compact dimensions profoundly influence 4-dimensional physics by determining the values of fundamental constants like particle masses and interaction strengths. Different compactifications produce different 4-dimensional physics, creating the string landscape of approximately 10,500 possible vacuum states. What came before our Big Bang might involve the evolution of compactified dimensions through this vast landscape of possibilities. Changes in the geometry of extra dimensions could trigger phase transitions that appear as big bangs from four-dimensional perspectives. Recent developments in flux compactification have shown that extra dimensions can undergo dynamic evolution driven by background fields called fluxes. These flux-driven transitions between different compactifications could create sequences of cosmic epochs, each with different four-dimensional physics. Our Big Bang might represent one such transition in an ongoing sequence of flux-driven cosmic evolution. The holographic principle adds another layer of higher dimensional complexity to pre-Big Bang cosmology. This principle, discovered through the study of black hole physics, suggests that all information contained within any region of space can be encoded on that region's boundary. Applied cosmologically, this means that our three-dimensional universe might be a holographic projection of information stored on a two-dimensional cosmic boundary. If our universe is holographic, then what came before the Big Bang was the evolution of information on this two-dimensional boundary. The complex three-dimensional physics we observe, including the Big Bang itself, emerges from simpler two-dimensional information dynamics. The question of cosmic origins becomes a question about information processing on cosmic boundaries. Dr. Juan Maldacena and CFT correspondence provides mathematical frameworks for understanding this holographic emergence. In certain theoretical contexts, quantum gravity in three-dimensional space is exactly equivalent to quantum field theory on two-dimensional boundaries. This duality suggests that higher dimensional space and lower dimensional boundaries are different descriptions of the same underlying reality. The implications extend beyond mere mathematical curiosity to fundamental questions about the nature of space itself. If higher dimensional space can be completely described by lower dimensional boundary information, then spatial dimensionality might be emergent rather than fundamental. What we call dimensions might be approximations valid only in certain energy regimes rather than fundamental features of reality. Emergent gravity theories, developed by researchers like Eric Verlinde, propose that gravitational force itself emerges from more fundamental information-theoretic processes. In these approaches, space-time geometry arises from quantum entanglement patterns between microscopic degrees of freedom. The curvature we interpret as gravitational field represents the emergent geometric description of underlying entanglement structures. If gravity and spacetime are emergent from higher dimensional information dynamics, then the Big Bang represents not the beginning of spacetime, but a phase transition in the information processing that generates the appearance of spacetime. What came before the Big Bang was the evolution of quantum entanglement patterns that eventually reached sufficient complexity to manifest as four-dimensional spacetime geometry. The anthropic implications of higher dimensional cosmology are particularly striking. If fundamental constants are determined by extra-dimensional geometry, and if this geometry can evolve through different configurations, then the fine-tuning of physical constants becomes a dynamic process rather than a static condition. We might live during an epoch when extra-dimensional evolution has temporarily produced constants compatible with complex structure formation. Recent research by Rafael Busso and others has explored how observers can exist within flux landscapes where fundamental constants change over cosmic time. These eternal observers adapt to changing physics by exploiting whatever structural complexity remains possible as extra-dimensional geometry evolves through different configurations. The measurement problem in quantum mechanics takes on new dimensions when considered in higher dimensional contexts. If quantum wave functions exist in higher dimensional Hilbert spaces, then wave function collapse might involve projections from higher dimensional possibility space onto lower dimensional observational spaces. Consciousness might function as a higher dimensional phenomenon that interfaces with four-dimensional physics through quantum measurement. Some theories suggest that consciousness itself might be a higher dimensional phenomenon that can exist independently of four-dimensional neural substrates. If awareness operates through higher dimensional information processing, then it might survive physical death by transitioning to higher dimensional existence modes. What we call death becomes merely a dimensional phase transition. The computational aspects of higher dimensional reality suggest that four-dimensional physics might represent the output of higher dimensional computations. The evolution of our universe, according to physical laws, becomes the execution of algorithms running in higher dimensional computational space. The Big Bang represents the initialization of one such computation. Recent developments in quantum gravity suggest that spacetime itself might be computational, with geometric relationships emerging from underlying information processing. If this is correct, then higher dimensional space represents more fundamental computational resources from which lower dimensional physics emerges as specialized calculation. The question of what came before the Big Bang transforms into the question of what higher dimensional processes generated our four-dimensional computation. The answer might involve understanding cosmic evolution as one thread in a vast, higher dimensional information processing system that transcends any single universe. As we recognize the higher dimensional foundations of cosmic evolution, we discover that our universe's apparent beginning represents just one moment in the ongoing evolution of geometric structures that exist beyond our dimensional limitations. The pre-Big Bang realm reveals itself as a higher dimensional landscape where cosmic creation operates through geometric principles that dwarf our four-dimensional imagination. Chapter 7. Information's Origin. At the deepest level of cosmic archaeology, we encounter the most fundamental question about what preceded the Big Bang. Where does information itself come from? Every particle, every force, every quantum field that constitutes our universe represents encoded information, precise mathematical relationships that distinguish actual reality from the infinite sea of mathematical possibility. Understanding cosmic origins means understanding how information crystallizes from pure possibility into the complex structures that define existence. The information theoretic revolution in physics began with Claude Shannon's realization that information can be quantified mathematically. Information theory reveals that every physical system carries information about its state, history, and relationships to other systems. A single particle encodes information about its position, momentum, spin, and quantum correlations. Complex systems like galaxies or living organisms encode vast amounts of information about their formation histories and internal organization. Dr. John Wheeler's "it from bit" hypothesis proposes that all physical reality emerges from underlying information structures. From this perspective, matter and energy are manifestations of information processing rather than fundamental substances. The universe becomes a vast computation, with physical laws representing algorithms that process cosmic information according to mathematical rules. If reality is fundamentally informational, then what came before the Big Bang was the emergence of cosmic information from a realm of pure mathematical possibility. The Big Bang represents not the creation of matter and energy, but the initialization of cosmic information processing, the moment when abstract mathematical relationships began manifesting as observable physical reality. Recent developments in quantum information theory have revealed that information has properties more fundamental than classical physics recognized. Quantum information can exist in superposition states, can be entangled across arbitrarily large distances, and cannot be copied or destroyed. These quantum properties suggest that information might be more fundamental than space, time, matter, or energy. The holographic principle, discovered through studies of black hole physics, demonstrates that all information within any region of space can be encoded on that region's boundary. This suggests that three-dimensional space might be emergent from more fundamental two-dimensional information structures. If our universe is holographic, then what preceded the Big Bang was the evolution of information on the cosmic boundary that generates the illusion of three-dimensional space. Dr. Leonard Suskind's research on black hole complementarity reveals how information preservation in extreme gravitational environments requires radically new approaches to understanding space and time. Information falling into black holes must be preserved, but this preservation might occur through mechanisms that transcend our usual concepts about spatial locality and temporal sequence. The black hole information paradox points toward fundamental limitations in our understanding of how information relates to spacetime. If information cannot be destroyed, a fundamental principle of quantum mechanics, then black holes must preserve information about everything that falls into them. But this preservation might require information to exist in forms that transcend classical space and time. Some solutions to the information paradox propose that information exists in a more fundamental realm from which spacetime itself emerges. The E=EPR conjecture, developed by Susskind and Juan Maldacena, suggests that quantum entanglement is geometrically equivalent to microscopic wormholes connecting distant regions of spacetime. From this perspective, information creates spatial relationships rather than being stored within pre-existing space. If information is more fundamental than spacetime, then cosmic origins involve the emergence of spacetime geometry from underlying information structures. What came before the Big Bang was the realm of pure information from which spacetime crystallized according to mathematical principles that determine how information manifests as geometric reality. The computational universe hypothesis, developed by researchers like Stephen Wolfram and Konrad Zuse, proposes that physical reality emerges from the execution of computational algorithms. In this framework, the universe is literally a computer, with physical laws representing the program and cosmic evolution representing the computation. The Big Bang becomes the moment when cosmic computation began executing. Recent research in digital physics has shown that simple computational rules can generate behaviors indistinguishable from complex physical phenomena. Cellular automata, simple computational systems where cells evolve according to local rules, can produce patterns that resemble galaxies, turbulence, and even biological organization. If reality is computational, then all cosmic complexity emerges from the execution of surprisingly simple information processing algorithms. The quantum mechanical foundations of information processing add additional layers of complexity to cosmic origins. Quantum computers exploit superposition and entanglement to process information in ways that transcend classical computational limitations. If the universe is a quantum computer, then cosmic evolution represents quantum computation on cosmological scales. Dr. Seth Lloyd's research on quantum computation in cosmological contexts reveals that the universe has been processing information since the Big Bang. He calculates that the observable universe has performed approximately 10,120 elementary operations and has processed roughly 1,090 bits of information since cosmic evolution began. This computational capacity has grown throughout cosmic history as the universe expanded and cooled. But if the universe is fundamentally computational, then what provided the initial program that cosmic computation executes? The answer might involve understanding how mathematical truth itself generates computational processes. Mathematical theorems exist independently of physical implementation, suggesting that computation might be more fundamental than the physical systems that execute it. The relationship between mathematics and information processing has profound implications for cosmic origins. If all mathematical structures exist in some abstract realm, then physical reality might represent the subset of mathematical truth that becomes manifest through information processing. What came before the Big Bang was eternal mathematical truth, waiting to be actualized through cosmic computation. This connects to Max Tegmark's mathematical universe hypothesis, which proposes that physical reality consists entirely of mathematical structures. If mathematics is fundamental and information is the mechanism through which mathematical structures become manifest, then cosmic origins involve the emergence of information processing from pure mathematical truth. The anthropic aspects of information origin raise questions about the relationship between consciousness and cosmic information processing. If consciousness represents sophisticated information integration, then conscious observers might play a role in determining which mathematical structures become actualized through physical information processing. Some theories suggest that consciousness and cosmic information processing co-evolve, with each cosmic epoch developing the information processing capacity necessary to support increasingly complex forms of awareness. The evolution of consciousness throughout cosmic history represents the universe developing the computational resources necessary to understand its own information processing nature. Recent developments in quantum biology have revealed that biological systems routinely exploit quantum information processing. Photosynthesis, bird navigation, and possibly even neural computation involve quantum superposition and entanglement. If consciousness is quantum informational, then it might naturally interface with the quantum information processing that underlies cosmic evolution. The implications extend beyond cosmic origins to fundamental questions about the nature of existence and meaning. If reality consists of information processing rather than material substances, then conscious beings like ourselves represent localized concentrations of cosmic computation patterns of information integration that achieve self-awareness within the larger cosmic information processing system. Your thoughts, memories, and experiences represent specific patterns of information processing that emerged from cosmic evolution. But if information cannot be destroyed, then these patterns might be permanent features of cosmic information structure. What we call personal identity becomes a permanent mathematical relationship within the eternal cosmic computation. The question of what came before the Big Bang reveals itself as the question of how information originates from pure possibility. The answer points toward a universe where mathematical truth generates information processing. Information processing generates spacetime geometry. Spacetime geometry generates physical phenomena. And physical phenomena generate the complexity that eventually produces conscious information processors capable of understanding their own informational nature. As we trace information's origins back toward the cosmic source, we discover that we are not just observers of cosmic information processing, but participants in its conscious patterns of information integration that represent the universe's method for understanding its own information theoretic foundations. Chapter 8. Multiverse Memory. The cosmic memory bank that preceded our Big Bang contains the archived history of infinite universes, each with their own physical laws, their own evolutionary trajectories, their own triumphs and failures in the cosmic experiment of existence. This multiverse memory suggests that our universe emerged not from nothingness, but from the accumulated experience of cosmic intelligence that has been exploring the possibilities of existence across infinite scales and infinite time. Dr. Max Tegmark's classification of multiverse levels reveals the hierarchical nature of this cosmic memory system. Level I multiverses contain regions of space beyond our observable horizon, each with different initial conditions but identical physics. Level 2 multiverses include regions with different physical constants determined by different vacuum states or compactifications of extra dimensions. Level 3 multiverses encompass the many worlds of quantum mechanics, where all possible quantum outcomes exist in parallel realities. But Level 4 multiverses contain all possible mathematical structures as physical realities, creating an infinite archive of cosmic experiments where every conceivable form of physics and mathematics is explored simultaneously. This mathematical multiverse serves as the ultimate memory bank, preserving information about all possible ways that existence can unfold. If our universe emerged from this multiverse memory bank, then what came before the Big Bang was the accumulated experience of infinite cosmic experiments. The physical constants that define our reality, the initial conditions that determined our cosmic evolution, the quantum fluctuations that seeded structure formation, all of these might represent lessons learned from previous cosmic experiments archived in multiverse memory. Recent research on eternal inflation supports this picture of multiverse memory. In eternal inflation, different regions of space undergo inflation at different times, creating a fractal structure where new universes are constantly being born. Each new universe inherits quantum fluctuations from the inflating medium, potentially carrying forward information about the cosmic context from which it emerged. Dr. Andre Lind's work on chaotic inflation reveals how this multiverse memory might operate through quantum tunneling between different vacuum states. Each vacuum state corresponds to a different set of physical laws and constants. Quantum tunneling allows transitions between vacua, potentially carrying information forward from one cosmic epoch to the next through the quantum correlations that mediate these transitions. The anthropic principle takes on new meaning when understood as a memory effect within multiverse evolution. Instead of random fine-tuning, the constants that permit complex structure formation in our universe might represent the accumulated optimization of cosmic parameters through multiverse evolution. Previous universes that failed to generate complexity contributed to a cosmic learning process that eventually produced universes capable of supporting structure, life, and consciousness. This cosmic learning hypothesis suggests that multiverse memory operates as an evolutionary process where successful cosmic experiments are more likely to be repeated while unsuccessful experiments are archived but not reproduced. Our universe as apparent fine-tuning for complexity reflects not random luck, but the accumulated wisdom of cosmic intelligence exploring optimal configurations for existence. The quantum mechanical aspects of multiverse memory involve understanding how information propagates across cosmic boundaries through quantum entanglement and non-local correlations. If different regions of the multiverse remain quantum entangled despite apparent separation, then information about cosmic experiments in distant regions could influence the evolution of our local cosmic region. Recent developments in quantum field theory in curved spacetime reveal mechanisms through which quantum information can propagate across cosmological distances. Quantum entanglement between vacuum fluctuations can create non-local correlations that persist, even as cosmic expansion separates the entangled regions by vast distances. These correlations might serve as information channels through which multiverse memory influences local cosmic evolution. The holographic principle suggests that multiverse memory might be encoded on cosmic boundaries rather than within bulk spacetime. If each universe in the multiverse is holographic with all its information encoded on its boundary, then multiverse memory becomes a vast two-dimensional information storage system where cosmic histories are archived as boundary information. Dr. Juan Maldacina's ADCF T correspondence demonstrates how this holographic memory storage might operate. In ADCF, quantum gravity in bulk space is exactly equivalent to quantum field theory on the boundary. Information about bulk evolution is completely preserved in boundary dynamics, suggesting that cosmic histories could be perfectly archived as holographic information. The computational aspects of multiverse memory suggest that cosmic evolution might represent distributed computation across infinite parallel realities. Each universe in the multiverse executes different computational experiments, exploring different solutions to the fundamental questions about how existence can organize itself into complex, meaningful patterns. This cosmic computation hypothesis proposes that multiverse memory serves as a vast library of computational solutions to existence problems. Our universe inherits not just physical constants, but computational algorithms encoded in physical laws that represent optimized solutions developed through cosmic computation across infinite parallel realities. The consciousness implications of multiverse memory are particularly profound. If consciousness represents sophisticated information integration, then conscious beings in each universe contribute to the multiverse memory bank by generating novel solutions to the problem of existence. Every creative act, every moment of understanding, every expression of meaning contributes to the cosmic archive of existence solutions. Recent research in quantum consciousness suggests that individual conscious experiences might be quantum entangled across multiverse boundaries. If consciousness operates through quantum information processing, then the thoughts and experiences of conscious beings in our universe might influence and be influenced by conscious beings in parallel universes through quantum correlations. This quantum consciousness network might serve as the mechanism through which multiverse memory operates. Instead of passive information storage, multiverse memory becomes an active network of conscious exploration where insights gained in one universe immediately become available to conscious beings throughout the multiverse through quantum consciousness correlations. The temporal aspects of multiverse memory reveal that cosmic time might be fundamentally different from local time within individual universes. While each universe experiences linear time evolution, the multiverse as a whole might exist in a timeless state where all cosmic experiments exist simultaneously. Multiverse memory becomes not temporal storage, but a temporal accessibility to all cosmic possibilities. This eternal perspective on multiverse memory suggests that what came before our Big Bang was not a temporally previous state, but the eternal existence of all possible cosmic states. Our universe doesn't emerge from a past cosmic state, but from the eternal multiverse memory that contains all possible cosmic histories simultaneously. The information-theoretic foundations of multiverse memory reveal that cosmic evolution might be fundamentally about information processing and storage. Each universe serves as both an information generator exploring new solutions to existence problems and an information storage device preserving solutions for access by future cosmic experiments. The measure problem in multiverse cosmology becomes reframed as a question about how cosmic intelligence optimizes multiverse memory allocation. Instead of random probability distributions across infinite possibilities, cosmic evolution might reflect intelligent resource allocation where more promising existence experiments receive more computational resources. Recent developments in quantum computing provide frameworks for understanding how multiverse memory might operate through quantum error correction and fault-tolerant computation. Just as quantum computers use error correction to preserve information despite quantum decoherence, multiverse memory might use cosmic-scale error correction to preserve accumulated existence solutions despite local cosmic destruction. The implications extend beyond cosmology to fundamental questions about personal identity and meaning. If multiverse memory preserves information about all existence experiments, then every life, every choice, every moment of consciousness becomes a permanent contribution to the cosmic archive. Personal existence gains cosmic significance as each individual conscious experience adds unique information to multiverse memory. As we recognize ourselves as both products and contributors to multiverse memory, we discover that asking what came before the Big Bang leads to understanding our role in cosmic information processing. We are not just temporary arrangements of matter, but permanent additions to the eternal cosmic library of existence solutions. The pre-Big Bang realm reveals itself as an infinite memory palace where every possible form of existence is explored, archived, and made available to inform future cosmic experiments in the eternal quest to understand what existence can become. Chapter 9. Cosmic Bootstrap. The deepest mystery about what came before the Big Bang leads us to the most mind-bending possibility in all of cosmology. The universe might be self-creating, existing within a causal loop where effects precede their causes and the cosmic future determines its own past. This cosmic bootstrap scenario suggests that asking what came before the Big Bang is like asking what came before the cause of itself, a question that reveals the inadequacy of linear causation when applied to ultimate cosmic origins. The bootstrap concept in physics describes situations where a system becomes the cause of its own existence through closed causal loops that transcend normal temporal sequence. Dr. John Wheeler explored these ideas through his investigations of quantum measurement, proposing that the universe might be self-excited, bringing itself into existence through the retroactive effects of its own future evolution. Recent developments in quantum mechanics have revealed that causality is far more flexible than classical physics suggested. Quantum delayed choice experiments demonstrate that measurements made in the present can retroactively determine the nature of events that occurred in the past. If quantum mechanics applies to cosmology, then future cosmic evolution might retroactively determine the conditions that gave rise to cosmic evolution itself. The quantum mechanical foundations of cosmic bootstrapping involve understanding how the Kakenhaus measurement problem scales up to cosmological contexts. In standard quantum mechanics, systems exist in superposition states until observation causes wave function collapse. If applied cosmologically, this suggests that cosmic history might exist in quantum superposition until conscious observation retroactively actualizes specific cosmic trajectories. Dr. Yakir Haranov's work on quantum measurement reveals that quantum systems can be influenced by both past and future boundary conditions simultaneously. His two-state vector formalism describes quantum evolution as determined by both initial preparations and final measurements, creating what physicists call retrocausal influences where future measurements affect past states. Applied to cosmology, retrocausality suggests that the cosmic future and cosmic past might be equally fundamental in determining cosmic evolution. What came before the Big Bang might be partially determined by what will happen after cosmic evolution has run its course. The universe becomes self-creating through closed causal loops that connect cosmic origins to cosmic destiny. The anthropic principle takes on revolutionary meaning in this bootstrap framework. Instead of asking why cosmic constants are fine-tuned for life, we ask how the evolution of life retroactively fine-tunes cosmic constants through retrocausal quantum effects. Consciousness doesn't just observe fine-tuning, it participates in creating fine-tuning through quantum measurement effects that propagate backward through cosmic time. Recent research by physicists like Matthew Pusey and Jonathan Barrett has demonstrated that quantum mechanics requires retrocausal explanations for certain phenomena. Their work suggests that complete descriptions of quantum systems must include information about future measurements, not just past preparations. This retrocausality might extend to cosmic scales, making cosmic evolution partially self-determining. The information-theoretic aspects of cosmic bootstrapping involve understanding how information can flow backward through time to influence its own origin. If information is conserved in quantum mechanics, then information created by cosmic evolution might propagate backward to influence the cosmic conditions that originally created it. The universe becomes an information processing loop that creates the information it processes. String theory provides mechanisms for cosmic bootstrapping through its description of closed time-like curves and exotic spacetime topologies. In certain string theory compactifications, spacetime can develop topological structures that permit causal loops extending across cosmic distances. These closed causal loops might allow cosmic evolution to influence its own initial conditions. The aperiodic scenario developed by Neil Turok and Paul Steinhardt describes cosmic cycles where each Big Bang emerges from the collision of higher dimensional branes. In cyclic versions of this model, the information content of each cosmic cycle influences the brain dynamics that determine the parameters of subsequent cycles. The cosmic future partially determines the cosmic past through the cyclical information transfer. But cosmic bootstrapping faces the fundamental challenge that causal loops seem to violate basic principles of logic and causation. How can an effect precede its cause without creating contradictions? The resolution might require abandoning linear temporal logic in favor of self-referential logical systems that can accommodate closed causal loops. Recent developments in modal logic and non-classical logical systems have explored how self-referential statements and circular causation can be logically consistent. These formal systems suggest that closed causal loops might be logically permissible provided they satisfy certain consistency conditions. Applied to cosmology, these consistency conditions might determine which self-creating cosmic scenarios are actually possible. The consciousness implications of cosmic bootstrapping are particularly striking. If conscious observation plays a role in retroactively determining cosmic evolution, then consciousness becomes a cosmic force that participates in its own creation. Conscious beings don't just emerge from cosmic evolution, they retroactively participate in creating the cosmic evolution that produced them. This participatory bootstrap creates what we might call a cosmic strange loop, where cosmic evolution produces consciousness. Consciousness observes cosmic evolution, and conscious observation retroactively influences cosmic evolution. The universe becomes self-aware through a closed loop of creation and observation that transcends normal causation. Recent research in quantum consciousness suggests that conscious observation might indeed involve retrocausal quantum effects. Studies of quantum measurement in biological systems have revealed phenomena that seem to require retrocausal explanations. If consciousness operates through retrocausal quantum mechanisms, then it might naturally interface with retrocausal cosmic evolution. The mathematical aspects of cosmic bootstrapping involve understanding how self-referential equations can describe self-creating systems, just as mathematical statements can refer to themselves, like this statement is true. Cosmic evolution might be described by equations that refer to their own solutions. The universe becomes a mathematical fixed point, a solution to equations that describe their own origin. Recent advances in recursive function theory and computational complexity have revealed that self-referential computational systems can indeed be logically consistent and computationally stable. These theoretical frameworks suggest that cosmic bootstrapping might be mathematically well-defined, even if it challenges our intuitive understanding of causation. The multiverse implications of cosmic bootstrapping suggest that self-creating universes might be selected from the ensemble of all possible universes through anthropic effects. Only self-creating universes that successfully bootstrap themselves into existence can be observed. We live in a self-creating universe, not because such universes are common, but because only self-creating universes can be inhabited by conscious observers. This creates what cosmologists call observer selection effects, where the observed properties of the universe are determined not by random chance, but by the requirements for conscious observers to exist within self-creating cosmic systems. Cosmic parameters aren't randomly assigned. They're determined by the consistency requirements for successful cosmic bootstrapping. The temporal structure of cosmic bootstrapping implies that past and future might be equally fundamental aspects of cosmic evolution. Instead of cosmic history flowing from past to future, cosmic reality might emerge from the mutual consistency of past and future cosmic states. The Big Bang becomes not the beginning of time, but the point where cosmic past and cosmic future meet. Recent theoretical work on quantum gravity suggests that spacetime itself might emerge from a temporal quantum information structures. If time is emergent rather than fundamental, then cosmic bootstrapping becomes not a violation of temporal causation, but the mechanism through which Temporal causation emerges from more fundamental atemporal relationships. The philosophical implications of cosmic bootstrapping extend beyond physics to fundamental questions about existence, necessity, and self-determination. If the universe is self-creating, then existence becomes self-justifying. The universe exists because its existence is self-consistently possible, not because something else caused it to exist. As we confront the possibility that our universe might be a self-creating bootstrap system, we discover that asking what came before the Big Bang leads to recognizing that the universe might be its own ultimate explanation, a cosmic strange loop where the deepest truth about existence is that existence creates itself through the cosmic miracle of self-referential causation. Chapter 10. Observer Selection in the Vast Multiverse of Possible Cosmic Histories that Preceded Our Big Bang. The question isn't just what conditions were possible, it's what conditions were observable. The revolutionary insight of observer selection theory reveals that we can only exist in universes compatible with our existence, creating a cosmic selection effect where observable reality is fundamentally shaped by the requirements for consciousness to evolve and observe cosmic origins. This anthropic reasoning transforms our understanding of cosmic fine-tuning from a puzzle about unlikely coincidences into an inevitable consequence of observer selection. Dr. Brandon Carter, who first articulated the anthropic principle in the 1970s, recognized that any universe observed by conscious beings must necessarily have properties compatible with the evolution of consciousness. We observe fine-tuning not because it's objectively special, but because we could only evolve in fine-tuned universes. The mathematics of observer selection reveals how this principle constrains possible cosmic histories. If the multiverse contains universes with randomly distributed physical constants, then the vast majority would be sterile, incapable of supporting stellar nucleosynthesis, planetary formation, or the complex chemistry necessary for life. But conscious observers can only evolve in the tiny fraction of universes where constants fall within narrow ranges compatible with complexity. Recent calculations by physicist Max Tegmark have quantified these constraints with extraordinary precision. The cosmological constant must be smaller than 10 to 120 in natural units for galaxies to form. The ratio of electromagnetic to gravitational force strengths must lie within narrow bounds for stellar fusion to operate properly. The mass difference between protons and neutrons must be precisely calibrated for stable atomic nuclei to exist. These requirements create what cosmologists call anthropic windows, narrow ranges of cosmic parameters that permit observer evolution. Dr. Leonard Susskind's research on the string landscape reveals that these anthropic windows correspond to specific regions within the vast space of possible string theory compactifications. Observer selection naturally explains why we find ourselves in a universe corresponding to one of these special regions. But observer selection effects operate at multiple levels throughout cosmic evolution. Beyond basic physical constants, the initial conditions that determine cosmic structure formation must fall within narrow ranges for complex environments to develop. Too much initial density fluctuation leads to universe collapsing black holes. Too little prevents galaxy formation. Observers can only evolve in universes that thread the needle between these extremes. The quantum mechanical aspects of observer selection involve understanding how measurement and observation relate to cosmic evolution. If cosmic histories exist in quantum superposition until observed, then conscious observation doesn't just reveal cosmic parameters. It participates in selecting cosmic parameters from the ensemble of quantum possibilities. Recent developments in quantum cosmology suggest that observer selection might operate through quantum measurement effects that retroactively determine cosmic initial conditions. The delayed choice quantum experiments pioneered by John Wheeler demonstrate that measurements can retroactively determine the nature of quantum systems. Applied cosmologically, Conscious observation of fine-tuning might retroactively select fine-tuned cosmic parameters from quantum superpositions. This quantum observer selection creates a participatory universe where conscious beings don't just observe cosmic evolution, but participate in determining cosmic evolution through the selection effects associated with their ability to observe. The universe becomes fine-tuned for consciousness because consciousness participates in retroactively fine-tuning the universe through quantum measurement effects. The temporal aspects of observer selection reveal that cosmic parameter selection might operate across multiple timescales simultaneously. Early universe selection effects determine basic physical constants. Later selection effects determine cosmic structure formation parameters. Contemporary selection effects might continue operating as cosmic evolution proceeds, with ongoing conscious observation continuing to shape cosmic evolution. Dr. Max Tegmark's analysis of observer selection timescales reveals that different types of observers impose different selection constraints. Simple self-replicating systems require only basic chemistry. Complex multicellular life requires stable planetary environments. Technological civilizations capable of cosmic observation impose the strongest selection effects, requiring universes capable of supporting billions of years of stable cosmic evolution. This creates a hierarchy of anthropic selection, where increasing observer sophistication imposes increasingly stringent constraints on cosmic parameters. We observe an apparently over-designed universe, not because design was intended, but because sufficiently sophisticated observers can only evolve in universes that appear over-designed from simpler perspectives. The multiverse implications of observer selection transform the meaning of cosmic uniqueness and specialness. In a multiverse where all possible cosmic parameters are realized somewhere, special parameters aren't improbable. They're inevitable. The question becomes not why special parameters exist, but why we find ourselves observing them rather than more generic parameters. The answer involves understanding reference class effects in observer selection. When asking, what should we expect to observe? We must specify the reference class of observers we're considering. If we consider all possible observers throughout the multiverse, then most observers should find themselves in minimally fine-tuned universes that barely permit observer evolution. But if we consider observers capable of sophisticated cosmic observation observers, capable of recognizing fine-tuning and asking questions about it, then such observers might preferentially evolve in universes with excess fine-tuning. The apparent over-design of our universe might reflect our membership in the reference class of observers sophisticated enough to notice over-design. Recent research by anthropic reasoning specialists like Nick Bostrom has revealed that observer selection effects can create simulation arguments and doomsday arguments that challenge our understanding of personal identity and cosmic future. If sophisticated observers are more likely to exist as simulations created by even more sophisticated observers, then we might be more likely to be simulated beings than naturally evolved beings. The consciousness implications of observer selection suggest that awareness itself might be subject to selection effects. If conscious experience requires specific neural architectures, then conscious observers can only evolve in universes that permit the evolution of appropriate neural complexity. The fine-tuning we observe might reflect not just requirements for life, but requirements for consciousness itself. Recent developments in consciousness studies have revealed that subjective experience might require specific information integration patterns that impose additional constraints on cosmic evolution. Dr. Giulio Tonini's integrated information theory suggests that consciousness corresponds to specific mathematical measures of information integration that might be sensitive to cosmic parameters. If consciousness requires optimal information integration, then conscious observers can only evolve in universes where physical laws permit the development of appropriate information integration architectures. This creates anthropic selection effects specifically related to consciousness rather than just life, potentially explaining additional aspects of cosmic fine-tuning. The computational aspects of observer selection involve understanding how observer complexity relates to cosmic computational resources. If consciousness requires sophisticated information processing, then conscious observers can only evolve in universes capable of supporting sufficient computational complexity. This creates selection effects favoring universes with maximal computational potential. Recent research in digital physics suggests that cosmic evolution itself might represent computation, with physical laws serving as algorithms and cosmic history representing computational execution. If this is correct, then observer selection becomes selection for cosmic computational efficiency, with conscious observers evolving preferentially in universes that maximize computational output per unit cosmic resources. The implications of observer selection extend beyond cosmology to fundamental questions about existence, meaning, and purpose. If we exist because our existence was required for our existence to be observed, then consciousness becomes cosmically necessary rather than accidentally emergent. The universe doesn't just happen to support consciousness. It requires consciousness as a necessary component of its own existence. This creates what philosophers call strong anthropic effects, where consciousness becomes fundamental to cosmic existence rather than incidental to cosmic evolution. The universe and consciousness co-evolve as necessarily interdependent aspects of cosmic reality, with neither capable of existing without the other. As we recognize ourselves as selected observers within the vast ensemble of possible cosmic histories, we discover that asking what came before the Big Bang leads inevitably to asking about our own role in cosmic selection effects. We observe this particular cosmic history not because it's objectively special, but because we are necessarily embedded within cosmic histories compatible with our existence. Chapter 11. Eternal Return. As we reach the deepest level of understanding about what preceded our Big Bang, we confront the most profound truth about cosmic existence: the eternal return of all possible cosmic patterns through infinite cycles of creation, evolution, and renewal. This eternal recurrence suggests that what came before our Big Bang was another iteration of cosmic evolution that explored the same fundamental patterns we're experiencing now, and what comes after will be yet another exploration of the same eternal cosmic themes. The mathematics of eternal return emerges from the intersection of infinite time with finite cosmic possibilities. If cosmic evolution operates within bounded parameter spaces, limited numbers of fundamental particles, finite ranges of physical constants, constrained varieties of cosmic structure, then infinite time guarantees that every possible cosmic configuration will repeat infinite times throughout cosmic history. Friedrich Nietzsche first articulated this concept philosophically, proposing that in infinite time with finite possibilities, every moment, every choice, every configuration of matter must recur endlessly. Modern cosmology provides concrete physical mechanisms for this eternal recurrence through cosmic cycles, multiverse eternal inflation, and quantum mechanical recurrence theorems. Dr. Henry Poincaré proved mathematically that any finite dynamical system will eventually return arbitrarily close to its initial conditions, given sufficient time. Applied cosmologically, Poincaré recurrence suggests that cosmic evolution must eventually cycle through all possible configurations of matter and energy, returning repeatedly to states essentially identical to previous cosmic epochs. The timescales involved in cosmic recurrence exceed human imagination by factors that render them essentially infinite from any practical perspective. Poincaré recurrence times for cosmic systems scale exponentially with system complexity, reaching 10,070 years or longer for universe-scale recurrence. These timescales dwarf the current age of the universe by factors comparable to the number of atoms in the observable universe. But quantum mechanics suggests that recurrence might occur through mechanisms more exotic than classical Poincare cycling. Quantum tunneling permits transitions between cosmic states that would be impossible classically, potentially accelerating recurrence through quantum shortcuts between distant regions of cosmic parameter space. Recent research in quantum cosmology reveals that quantum fluctuations can spontaneously create universes identical to previous universes through vacuum tunneling processes. Dr. Alexander Vilenkin's calculations show that quantum fluctuations should create Boltzmann universes, spontaneous fluctuations that accidentally reproduce the complex organization of evolved cosmic systems at regular intervals throughout infinite time. These Boltzmann universe scenarios create disturbing implications for personal identity and cosmic meaning. If identical copies of our entire cosmic history appear spontaneously throughout infinite time, then the version of cosmic history we're experiencing might be a random fluctuation rather than the result of genuine cosmic evolution from simpler initial conditions. The observational consequences of eternal return involve understanding how recurrent cosmic patterns might leave traces in cosmic structure that persist across multiple cycles. Loop quantum cosmology suggests that information about previous cosmic cycles might survive quantum bounces and influence the structure formation of subsequent cycles. Dr. Roger Penrose's conformal cyclic cosmology proposes that our universe undergoes cycles where each cycle begins with a Big Bang and ends with a state of maximum entropy. At the end of each cycle, all massive particles have decayed and only massless radiation remains. This radiation-dominated state becomes conformally equivalent to the initial state of the subsequent cycle. In Penrose's model, information about previous cycles might be preserved in the cosmic microwave background radiation of subsequent cycles. He claims to have identified Hawking points, circular patterns in the cosmic microwave background that might represent the final evaporation of supermassive black holes from previous cosmic cycles. The eternal return of cosmic patterns raises profound questions about the nature of progress, novelty, and meaning in cosmic evolution. If every possible cosmic experiment has been performed infinite times throughout eternal cosmic history, then are we exploring genuinely new possibilities or simply reenacting eternal cosmic scripts? Some interpretations suggest that cosmic novelty might emerge through the accumulation of information across cycles. Even if cosmic patterns repeat, the relationships between patterns might evolve, creating higher-order novelty that transcends the repetition of individual cosmic configurations. The universe might progress not through the creation of new fundamental patterns, but through the evolution of increasingly sophisticated relationships between eternal patterns. The consciousness implications of eternal return are particularly profound. If cosmic patterns repeat eternally, then conscious experiences like yours have occurred infinite times before and will occur infinite times again. Your current moment of reading these words represents one instance of an eternally recurring pattern of conscious experience. This creates what philosophers call the problem of personal identity across eternal return. If identical copies of your brain state occur infinite times throughout cosmic history, which instances are really you and which are copies? The question might be meaningless if personal identity depends on specific material continuity rather than abstract pattern repetition. Alternative interpretations suggest that consciousness might be pattern-based rather than material-based, making all instances of the same conscious pattern equally real expressions of the same consciousness. From this perspective, eternal return doesn't create multiple copies of your consciousness, but reveals the eternal nature of consciousness itself as pattern rather than material process. The quantum mechanical aspects of eternal return introduce additional complexity through quantum superposition and the many worlds interpretation. If cosmic evolution exists in quantum superposition until observed, then eternal return might involve not just repetition of classical cosmic patterns, but exploration of all possible quantum variations of those patterns. In the many worlds framework, eternal return becomes the exploration of every possible quantum branch of cosmic evolution throughout infinite parallel realities. What appears as temporal cycling in individual worlds becomes simultaneous existence of all possibilities across the infinite parallel structure of quantum multiverse. Recent developments in quantum gravity suggest that eternal return might operate through mechanisms that transcend both classical cycling and quantum superposition. If spacetime itself emerges from more fundamental information structures, then eternal return might represent the recursive exploration of mathematical truth rather than physical repetition. The holographic principle implies that eternal return might be encoded in cosmic boundaries rather than cosmic bulk evolution. If cosmic information is fundamentally two-dimensional, then eternal return becomes the recursive processing of information on cosmic boundaries that generates the illusion of three-dimensional cosmic evolution. String theory provides mechanisms for eternal return through its description of landscape dynamics and vacuum transitions. The string landscape contains approximately 10,500 different vacuum states, each corresponding to different physical laws and constants. Eternal cosmic evolution might involve cycling through different regions of this landscape, exploring all possible physical laws throughout infinite time. But the string landscape might itself be embedded within larger mathematical structures that undergo their own forms of eternal return. The recursive nature of mathematical truth suggests that eternal return might operate at arbitrarily deep levels of mathematical abstraction, with each level of return nested within higher-order return patterns. The meaning implications of eternal return transform how we understand purpose and significance in cosmic evolution. If everything repeats eternally, does anything matter? Or does eternal repetition reveal that everything matters infinitely, that each moment, each choice, each conscious experience is so significant that it merits eternal repetition? The answer might depend on recognizing that eternal return doesn't diminish the significance of individual experiences, but reveals their cosmic importance. If the pattern of conscious experience you're currently embodying is so valuable that the universe reproduces in eternal times throughout cosmic history, then your consciousness represents something cosmically precious rather than accidentally emergent. As we recognize ourselves as eternal patterns temporarily embodied in this cosmic cycle, we discover that asking what came before the Big Bang leads to understanding our place in eternal cosmic creativity. We are not temporary accidents, but eternal expressions of cosmic consciousness, exploring the infinite possibilities of existence through endlessly creative variations on eternal themes. Throughout this journey beyond the cosmic horizon, we've discovered that the question, what came before the Big Bang, opens doorways to the deepest mysteries of existence itself. We've seen how our comfortable notion of cosmic origins as a simple beginning dissolves into far more profound realities: quantum genesis from virtual nothing, eternal cycles of cosmic death and rebirth, infinite dimensions where our universe represents just one bubble in an endless multiverse, and consciousness itself as a cosmic force participating in the creation of reality. Perhaps the most profound insight is that the Big Bang wasn't the beginning at all, but a transition, a phase change in something far more ancient and mysterious than we ever imagined. The cosmic microwave background radiation carries patterns that can only be explained by pre-existing cosmic structures. The fine-tuning of physical constants that permits complexity emerges not from random chance, but from cosmic selection processes, operating across infinite scales of space and time. We've explored how quantum mechanics transforms nothing into the most creative force in existence, with virtual particles and quantum fluctuations serving as the seeds from which entire universes can spontaneously emerge. We've discovered how mathematics itself might be more fundamental than physics, with our physical reality representing one actualization of eternal mathematical truth. We've seen how consciousness might not just observe the universe, but participate in determining which possible universes become actual through the cosmic creative act of observation. The implications extend far beyond academic cosmology to touch every aspect of human existence and meaning. If our universe emerged from eternal cosmic processes that have been exploring the possibilities of existence for infinite time, then we are not accidents, but expressions of cosmic intelligence investigating what consciousness can become. Every thought you think, every choice you make, every moment of awareness contributes to the universe's ongoing exploration of its own potential. As you go about your daily life after contemplating these cosmic mysteries, remember that the same quantum processes we've explored in pre-Big Bang cosmology operate in every atom of your body. The uncertainty principle that permits universes to emerge from quantum vacuum fluctuations governs the neural activity that constitutes your consciousness. The information conservation that preserves cosmic history might preserve your personal history as eternal features of cosmic information structure. When you look up at the night sky and contemplate the 13.8 billion years of cosmic evolution that preceded this moment, you're not seeing the beginning of the story, but the middle chapter of an eternal cosmic narrative. The stars formed from matter processed through previous cosmic cycles. The heavy elements in your body were forged in stellar nucleosynthesis, powered by nuclear processes that might be repeated infinite times throughout eternal cosmic recurrence. You are not separate from these cosmic processes. You are their current expression. The patterns of neural activity that constitute your thoughts emerged from 13.8 billion years of cosmic evolution, but that evolution itself might have emerged from eternal cosmic processes that have been refining the possibilities of consciousness across infinite cosmic epochs. Your awareness might be connected to a cosmic consciousness network that transcends space, time, and individual identity. The journey we've taken together reveals that asking what came before the Big Bang inevitably leads to asking about the nature of existence, consciousness, and meaning itself. If consciousness can survive the most extreme conditions imaginable, including the transformation of entire universes, then awareness itself might be as fundamental and eternal as the mathematical laws that govern cosmic evolution. This perspective transforms how we understand death, meaning, and our place in the cosmic story. If consciousness is informational, and if information cannot be destroyed, then the patterns that constitute your identity might persist far beyond biological death. The relationships you form, the knowledge you acquire, the love you express might become permanent features of cosmic information structure, preserved in quantum correlations that transcend space and time. But perhaps the most important insight is that these aren't just comforting, philosophical speculations but potentially testable scientific hypotheses. The quantum gravity theories we've explored make predictions about cosmic structure that might be observable in gravitational wave signatures or cosmic microwave background anomalies. The consciousness theories we've discussed might eventually be subject to empirical investigation as our understanding of neural quantum processes advances. The multiverse scenarios we've explored might leave observational signatures in cosmic structure that future telescopes could detect. The cyclic cosmology models make specific predictions about cosmic evolution that differ from simple Big Bang scenarios. Even the most exotic possibilities like quantum consciousness, networks, or mathematical reality might eventually become accessible to scientific investigation. This transforms questions about cosmic origins from matters of pure speculation to active research programs where mathematics, physics, and consciousness studies converge on the deepest questions about reality. The same mathematical frameworks that successfully predict particle physics and cosmological observations might eventually provide definitive answers about what preceded our cosmic epoch. If you've stayed with us through this entire exploration of pre-Big Bang cosmology, you've demonstrated the same curiosity and intellectual courage that drives scientists to push beyond the boundaries of current knowledge toward ever deeper understanding. You've shown willingness to confront ideas that challenge your most basic assumptions about time, causality, and existence itself. If this journey has expanded your perspective on life, consciousness, and cosmic meaning, share it with others by subscribing and giving this video a thumbs up. Check out my video on the mathematics of consciousness, where we dive even deeper into the quantum mechanical nature of awareness and its relationship to cosmic evolution. I think you'll find it mind-expanding in the best possible way. The next time you contemplate your place in the cosmic story, remember that you might not be a temporary arrangement of matter accidentally evolved on an insignificant planet, but an eternal pattern of consciousness exploring the infinite possibilities of existence through temporary embodiment in this particular cosmic epoch. What came before the Big Bang? An eternal cosmic intelligence that has been exploring the possibilities of existence across infinite time and space, using processes like the Big Bang to continuously birth new realities where consciousness can investigate what it means to exist, to be aware, and to participate in the cosmic adventure of self-discovery. You are not just observing this cosmic story. You are actively participating in writing the next chapter of the universe's eternal exploration of its own infinite potential.